Have Professor Hemant Chouhan from Ahmedabad University who will talk about the journey of bulletproof jacket development. Please welcome Professor Chauhan.
Thank you. Good afternoon, everyone. Thanks. This time I'm in a different role since morning. Okay, so for last more than a decade, I have been working in the domain of bulletproof jackets towards the development of actually bulletproof. So I'll take you through a small journey wherein how in the last more than 100 years, but I'll keep it short, that history part of it. So it all began somewhere in 1500, 1600 series of the years. But in the modern world, somewhere around 1901, the first West was actually tested. So just 125 years back, this was the way the testing was done. And this is a classic image, the second one, wherein in 1923 in Washington, a design was made to conduct a test against that time's bullet, and it was in between the two world wars that the entire bulletproofing phenomena came into existence. Early good old days, leather and silk was the only primary material. Slowly steel, metal came into picture. In the modern era, what you or majority call as aramid or the Kevlar we know. So late in 90s and till last decade, I would say, or last 15 years back, aramid was the commonly known as Kevlar was the key material. Present date, we are not dependent on any single material system. It's going to be a hybrid. We will discuss one by one all of them. But primarily it is ultra high molecular weight polyethylene and ceramics. So present day, the technologies changed a lot. Okay. Before studying any issue, I call it as a virus. So if you have to develop an antivirus, first you should understand what the virus is. So in Indian context, this facility or this thing was defined as standard. So generally we follow US or the global standards, but fortunately in 2018, Indian standards were defined. So as you can see here, we have designated them as BIS level 1 to level 6. So for your ease, I have mentioned which weapon. If it is a pocket held weapon, probably it's a 9 × 19 mm. So you call it as a pistol. This is the smallest possible threat, and you should know that, okay, there is a speed associated with that, and there is a mass of the bullet. And of course, there are some testing parameters, so you can leave that. AK-47 you keep on hearing in news and whatnot. Why so? Because it's an interesting weapon. It's short in size, it has got a good range, relatively light in weight, and it has got two locations at BIS level 2 and BIS level 5. You've got the same weapon. If I have to tell you, there are two different types of bullet, or at least for now we'll consider two. There are actually more than dozen. BIS level 2 has got 7.62 × 39 mm. This is a mild steel core bullet. If I have to differentiate between mild steel, I have to I know there are few audience from non-engineering background. So mild steel is just like the door frame, whereas your kitchen knife is a hard steel. So it's really difficult to make a scratch on a kitchen knife, whereas you can comfortably make a scratch on any door or any general purpose steel piece. So this BIS level 2 is all about mild steel core, and we can comfortably stop it with the help of plastics and polymers. Whereas BIS level 5 used to be innovation by these three nations, that is us and our two of our closest ones. So we replaced rather the core inside the bullet, which we'll see in the upcoming slide. What do we mean by that? With a harder material system. In between, we have an international standard weapon that is 7.62 cross 51 mm, also known as NATO ball. There could be variety of weapons to fire it, but it's the bullet dimension that defines that, okay, what kind of threat you are carrying, because the weight is 9.5 and your speed would be 840. This used to be all lead, but now all are using steel in that. Then INSAS, army is not concerned, so I worked at IIT Delhi for all this matter, and INSAS was never a concern for these army people. It was primarily AK-47 hard steel core. In Indian context, we call it as Khirki bullet, Pune. And the last one is sniper, maybe for the movies and other reasons you might have heard of. A weapon which can act as a point blank from a range of 1,000 meters. A human standing 1 kilometer away is as good as a 9 mm pistol touching your skin. That is the power of a sniper, which we'll see in the upcoming slide why so. And there goes the higher speeds as well. So I presume we all are very much on the same page as far as virus is concerned. This is derived primarily from the US standard. So in the US standard, that is NIJ, level 2A, level 2, until the end of 3A, that is 0.44 Magnum. All bullets can be stopped by a soft armor barrel. They are easy to stop, relatively easy, or we call them as these are pocket-held weapons. After that, they directly have an international standard, NATO standard bullet, that is 7.62 cross 51 mm or M80 NATO ball, and then US has got APM2. They call it simply M2, that is their US standard sniper. India generally followed Russia for that matter, so we follow Russian Dragunov. So we have a slightly different this version, we call it 54R API, that is armor piercing incendiary. Now to understand what do we mean by that, because we are not going to stop one bullet. So what is the kinetic energy of one? So over here, if I look at this, it is just below 700 joules of kinetic energy. If I go to this AK-47, it is above 2000. If we go for the international standard, it is above 3000. But this is really dangerous. It has got the hardest possible, which we'll see in the upcoming slide. The bullet is the most lethal one. And in reality, the energy approaches 4000 joules. 150 joule is more than sufficient to kill a human. Impact, a head injury is more than sufficient to kill a human. We are talking somewhere close to 4000. So that is the power of the so-called bullet. Now what is inside this bullet? So we used to machine them, we are engineers, so we cut them. We want to know what is inside this virus. So we learned that, okay, mild steel has got a relatively flatter shape surrounded by some blackish material that happens to be lead. And of course, to increase the life of the barrel, steel barrel, we always provide a brass or a copper jacketing. That is what we call as the FMJ, full metal jacketed. That is basically a covering of brass so that my barrel is not worn. If both the steel is there, that is the barrel as well as the bullet is a steel, then my barrel won't last very long. If we cut the complete bullet, we found that, okay, there are variety of cores inside. So if we look at only the left side of it, this tip is very sharp compared to the other one, which is this bottommost mild steel is an international standard AK-47 bullet, which is a mild steel core bullet. Whereas this one, it's available only with India and two of the northern region neighbors. If we look at the hardness, typically the hardness of mild steel, MSC is 20 to 25, whereas for HSC it is 50 plus minus 5. So unfortunately, no plastic can handle this kind of tool or this kind of hardness at that given energies. And if we look at the sniper, it is even harder. To give a scientific challenge, in India, we do not produce the core. This particular pin you can see, this is what we call as the steel core of a projectile or the bullet. We are still date not producing this 65 plus minus HRC core. We import it and then we convert it into a bullet, or we directly import the bullet completely. So that way the shape, the size, the material is the most important, and not that outside yellow colored material, the brass. It is the inside that counts, and the hardness is the key, because we can comfortably stop the brass and the lead. But when it comes to the hardness of the steel, that becomes a real challenge. And if I know what you are wearing, the other person is wearing, you just need to increase this powdered part, which happens to be the explosive. So let's say you are having a Indian AK-47 HSC. So the speed is 710 meters per second. If you increase the weight of the explosive by few milligrams, your bullet will be moving at a speed of say 750, and you designed a jacket for 715 or 710 plus minus 15. So that is where the things matter. So we are looking for two types of panels. One is soft armor panel, which is close to the human body or touching the human body. In general, it is termed as the vest. So if someone is wearing it, you won't be able to differentiate that if he is wearing it or not. Whereas a hard armor panel, which is the front side in this figure, it has got so many components. The two primary things are, first, we need to erode the steel part. Second, we need to stop the debris of the steel as well as whatever we have broken in the name of stopping this projectile. So we have boron or silicon or aluminum oxide, as in ceramics. It could be single material or hybrid. That is the front part of it. Basically, we look to either break the bullet, grind the bullet, blunt the bullet. Those are the only ways that we can limit it. In the process, we will end up damaging this ceramic. If I am having a cup of tea and I drop it, that too is a ceramic. So ceramics are extremely brittle or very poor in tension. So they can't take bending loads, they can't take tensile loads, so that will break. So there will be a lot of crushing. Now we need to trap that entire crushed ceramic along with the debris of maybe two or more than two pieces of grinded bullet. Those needs to be stopped. So we need a backing, and over there we solely rely on fiber reinforced composites. Earlier this used to be Kevlar, now we don't prefer that. Companies are using it for, of course, the commercial cost reasons, but UHMWP happens to be the best serving material. In engineering, if you are doing something, design is a must. So finite element based simulations or designs are the first step to start with, but unfortunately, I said unfortunately because in balastics we don't know the answer. Fortunately, in all other engineering domains, we are not designing the product to damage it. We design the product such that it remains within the yield limit. We always look for that the loading will be well within the modulus of elasticity of a material system, and in case of bullet, we are very much sure that the very loading point would result in damage, that is crossing the ultimate tensile or ultimate compression, the ultimate strength point basically. So the challenges are multifold. Still, you need to characterize what materials you are having, determine all possible properties with respect to a balastics model, and then let's see how your things are working. So at the top we have got a ceramic layer, and at the back we are planning for some UHMW, define all the properties. Yet it might not do like that, because when I fire single bullet, the bullet is stopped and I can see so many cracks. So can I fire a second bullet? Because there are many unanswered questions. In reality, a panel will be tested against either 6 bullets or 8 bullets. So if it's a sniper, it's a 6 bullet, 9 mm will be a 6 bullet, in between all will be tested against 8 bullets, which is quite a large number, and it is assumed or it is expected that a human is wearing a 1000 centimeter panel, that is the human chest area, and 8 bullets are to be fired within this smaller space. And needless to tell, one bullet is more than sufficient to kill a human. So there are many unanswered, and how these cracks will propagate, what kind of damages will happen. So designing becomes challenging. And as Professor Shyam mentioned, he is going to teach these aspects of design in the course of Masters of Composite. So here we see what happens. The important thing is how time plays a critical role. 100 into 10 to the power minus 6 was the time, the bullet is completely either stopped or perforated. So either the life is saved or killed. So we simulate that what happens when the bullet velocity increases and at what point of time or at what speed of this projectile there will be a perforation. That can be converted into the kinetic energy profiles. So we designed a system at least 735, 710 plus minus 15. So that brings us to 725 kind of. So you can precisely calculate and design. But again, something unique with the composites is that it's not a metal. Had it been metal, we could have casted it and rolled it. Things would have been uniform, but here every specimen is to be made precisely. So that way things are challenging and we could precisely calculate that, okay, what should be the thickness of the given material. Moving on, what material? So we already mentioned that, okay, material is important. Everyone is moving from metals or homogeneous materials to composites for the directional properties. Now this particular slide gives, or this particular image I would say, since it was created by Honeywell, so that's why it says Spectra. Spectra is basically the commercial name of the ultra high molecular weight fiber grade developed by Honeywell, USA. So we see steel is somewhere at the bottom. Okay, modulus and tenacity are two things which are always not in proportion. So you try to increase one, someone will go down. Whereas in belastics, steel we can't change. What it is, it will remain the same. Glass, there is a positioning and you can't expect much. What we are expecting that the tenacity, the definition if someone is not clear about, and modulus, both should be as high as possible. So that is where the entire game changed. That Kevlar, when came into existence, it was very good material, but now we have reached the limiting condition of the polymer chemistry of Kevlars. So it can't move ahead much. Whereas UHMP started close to Kevlars and now it is moving up. Both the modulus and tenacity, that is the diameter is decreasing, density is decreasing and strength is increasing. So that is the beauty of UHMWP. Kevlar is the second best material, but there are few issues with that, yet it is required. For few specific reasons, Kevlar is required. So what specific attribute? This high strength, excellent chemical resistance. By the way, let me tell you, UHMWP is that simple plastic bag which you carry for the household stuff. It's only the ultra high molecular weight of this polymer change that matters. Otherwise, it's just a polyethylene, the bag of polyethylene. The density of a UHMWP made composite panel is 0.97. Water is 1. So that way, it also serves the purpose of floating a human body. It helps in actually crossing the river or it won't let you drown in a accidental case. And plastics are not happy with water, so they are hydrophobic in nature. They repel it, whereas Kevlar absorbs, or the properties of Kevlar deteriorate when exposed to UV or sunlight and moisture. Whereas UHMWP is not at all affected by moisture, though light might affect, but not much study is available. The biggest benefit associated with UHMWP is its ballistic resistance, that is the bulletproofing capabilities, other than the other properties. Now, what should be, in what form we should use? So the most common one known to us are like 2D woven. So we'll have two fibers, one moving along x-axis, another along y-axis, and they are intertwined with each other the way this image shows. So there is a warp and a weft fiber. But the issue with the system is one of the fiber, if kept straight, the other one will have to move like a wave. So in that case, you are not exploiting the best possible properties of that material. So that is the reason that in case of UHMWP, we look for UD ply, that is unidirectional plies. So this figure shows most of the commercial grades of UHMWP, they have 4 plies of 090, 090, and that makes one thin layer of fabric. And if we cut a ply and see a scanning electron microscopy, then this is how they look like. So the long pipe type of things, they are the longitudinal fiber and all the circles are the 90 degree, that is the perpendicular fiber. This is how the fabric looks like, and this is of course a tested laminate. Still, what is the biggest challenge? As we know, it's a plastic. So melting point is, of course, it is somewhere around 142, 144 for polyethylene. So beyond that temperature, things are in trouble, and hardness of bullet, which is beyond our control because it will be fired. So the moment we say that we are exceeding the limits of 25 HRC or mild steel core bullet, plastics can't handle that much of. We can increase the thickness, we can restrict or limit the kinetic energy had it been a lead or a mild steel. But since it's a hard steel bullet, AK or a sniper, these materials are not going to serve. Yet we need to stop the bullet. So we studied variety of materials, means the mankind. Steel is the best possible option, but the density is the biggest challenge, 8,000 almost. So the best outcome came in the form of ceramics. Ceramics have some unique properties that they have very good compressive strength, they have the ability to wear any material. The only challenge associated with ceramics is they are very poor in bending and tension. So if there is any kind of bending phenomena, the strain to failure is very, very low. So the moment we will try to press the bullet inside, it will develop a brittle failure or brittle crack in the material. The most commonly used materials for this case are boron carbide, silicon carbide, and to some extent aluminum oxide as well. Presently, the cost efficient solutions are comprising of a hybrid of boron and silicon, because boron is very costly and silicon is slightly less, but the density of silicon is slightly higher than boron. So it's like a compromise between the cost and the technology. If you want to go for the best possible solution, go with boron carbide, but then the costs are highest possible. And many of the studies were done to see how the penetration happens in this case. So the projectile damages ceramic at its leading surface. So in this figure, these are the few of the earlier ones, that how the material gets lifted, how a cavity is created, the fragmentation will be done, and there will be zone wherein the material will try to bend and cracks will initiate. But we need to stop that. I mean, this is unavoidable. So in the next figure, we'll come to know what exactly is the mechanism. The moment the bullet hits, there will be a zone of compression. So there is a projectile. When it touches the ceramic, it will try to create a zone of compression. As a result of this compression, a stress wave will travel through the depth direction, along the depth direction till the end of the specimen, and that will lead to shearing, compression of the material ahead of it. So that will result into pulverization, converting the ceramic back into powder or pieces at least. In turn, that will lead to compression, and that means tensile phenomena. We are trying to bend a specimen, and we already discussed that ceramics are very poor in tension. If I have that teacup, I can't bend it. Had it been a plastic, I can comfortably bend it. So as a result, there will be a lot of damage. Now, the good part is my tip of the bullet is damaged because of this abrasive tool. Lot of material of high hardness, that steel, is quite worn, that is grinding phenomena is done, but now we have got lot of debris of this ceramic along with two or more than two pieces of left out bullets, which are still moving at a very high kinetic energy. So at the back of that, will place a backing material, and that backing material can be ultra high molecular weight polyethylene. And this is how either a crack will grow like this. So here we can see that, okay, there is a bending phenomena. Part of material is trying to remain there and a part is being pushed. So a specific type of cone will be created depending on the composition and the processing, what we have done with the ceramics. And in turn, this tip of the bullet will perform the phenomena of grinding or pulverization of the material in front of it. These are few of the very critical studies wherein it was studied with the fast flashing X-rays that how the crack propagates. So we observed the radially outward moving as well as the circumferential, circular kind of cracks. When a bullet hits, this entire ceramic is one piece. So we can see the crack extending till the edges. And that very figure confirms that second and third bullet is not a very good idea. Because if unfortunately, if I say that at this point next to D, My red marker is the spot of bullet. So we can comfortably appreciate this fact. It has got a good space to move in between a cracked line. So perforation is possible. If not second, maybe third, maybe fourth, we have to go till 7 and 8. In another study, it was studied with in the perpendicular direction what happens. So it was primarily to study how much material of ceramic is lost and what kind of damage and deformation with respect to time the projectile is going through. APM2 moves at a 860, 870 meters. So the time requirements are going down. Within a very short span of time, the entire phenomena is over. So now let's come to the manufacturing. I won't touch deep into, I knew that many of the presenters before me have discussed this. So this is a unique system which was primarily developed for automobile industry, but in the processing of polymer based composites, compression molding is the key process for processing of UHMWPs or even Kevlars. So this is one of the cycle which we use to make. The difference is that the pressure required here are very, very high. And why I mentioned pressure, for temperature processing of any material, the temperature might be defined by the OEM, the supplier of the raw material. In a study, what we did, we performed the compression molding at a pressure of 34.5 bar or constant, we kept the grade constant, and for the very obvious reasons I can't declare the grades here. So we found that the strength of this material is somewhere around 450 megapascal. Then we increased, the temperature remains constant, the processing time was 30 minutes. We increased the pressure by 4 times. So basically I am having, let's say, 10 layers of a material. Earlier that was pressed at 34.5. And in the another specimen or another cycle, it was pressed at 4 times the pressure, that is 138 megapascal. And we observed that the strength has increased from almost 450 to nearly 600 megapascal. Now this is the beauty that many starts the business of balastics and bulletproofing. They say that we know how many layers are required and we'll make it. But we miss to optimize the processing parameters, and there is a very thin line or there is a very small zone of optimal processing area, what we call as. So that is how these things matter. And when you make a product at a less optimized parameters, then to study that, we conduct non-destructive testing. So this is an image of an ultrasonic C scan. Those who are from the subject, they know, yesterday we had a full lecture on this NDTs. So ultrasonic C scan has got both, 3 of them, A scan, B scan and C scan. And in C scan, we can see this should have been completely, this part is the neck protection, the HAP part of human body neck to be protected. The shape, blue color is pretty clear that, okay, where is my hand is the location, but I can see a lot of whites here. It means lack of pressure or incomplete consolidation of the material. Had it been the perfect one, all reds and whites, reds means defect and whites mean inappropriate consolidation. If it is a perfectly consolidated material, then the outcome of a C scan would be a completely blue screen, something like this. Though it has got couple of defects, but they might not be visible. Okay, over here I can see something just above my cursor. So these type of very fine defects are acceptable, but not the previous screen. Now how to integrate ceramics with UHMWPs. So in one of the image we have seen that if the ceramic plate is integral, that is one piece, or we call it as the monolithic ceramic, then one bullet is sufficient to generate cracks till the end. So what we did, we took 30 mm hacks or 30 mm square tiles, so that when a bullet hits, only a small group of maybe 1 or maximum 7 tiles, that is 1 at the center and 6 touching it, will be damaged. Other sides are at least safe. And the process required here is, you should first have your compression molded UHMWP laminate ready, and then there is an entire series what we call as the process of autoclave. So many of the presenters before me have discussed, I won't go into that. We need to apply a suitable glue on top of UHMWP. appropriately treated ceramic, wrap it with this yellow color is all about Kevlar. Now this also is a unique phenomena. You need one layer of Kevlar. When we are spending so much on UHMWPs, we could have skipped Kevlar for one layer, but the properties we are getting and the the resulting outcomes, they are well met by Kevlar, not by UHMWP. So there we have to study and optimize our system, and this is a cycle which we follow for autoclave. So with that, we come to a point wherein we got a BIS level 2 and level 3 panel. BIS level 2 and 3 means MSC AK-47 and this M80 NATO ball. Whereas level 5 and 6 is AK-47 hard steel and a sniper. So this is how the panels look like. If you are interested, you can contact me later. I have it. Testing. If you have a panel, go for the testing. So it feels like that, okay, we should have a weapon, fire it and over. It's not over. There is a BIS standard and there is a test protocol, and that is really very, very rigorous. Why so? Because we made a panel today and we will test it tomorrow. Definitely the bullet will stop. But maybe the panel will be used 5 years from now, or it was being used but there was no bullet hit luckily. What is the condition of the panel 5 years from now? So for that we have an aging cycle. There is a 11-day thermomechanical conditioning cycle, wherein in the span of a very short 11-day cycle, it is equal to 5-year lived ballistic panel, and then testing is to be done. So generally a fresh made panel on 12th day may fail. Likewise, an army man may have to cross a river body, or there could be shower at any moment of time, like we are crossing every now and then. So if wetted, because in case of steel there was no issue, then came Kevlar. For almost 30 years Kevlar was the boss, market leader, and it was very well affected by moisture. So there was a scheme for, in internationals it is 1 hour 60 minutes, and in Indian standard it is now 30 minutes, because of the obvious reason that now we have technologies to seal the panel perfectly. So there is no scope of water ingress. None of the test agency allows you to take a picture, but for your understanding, I took pictures from some of the army base and they are unnamed, so it's fine. The standard is 10-meter distance, so there will be a tip of the barrel from which the bullet will exit, and exactly at 10-meter distance should be your target. Over there, we place a chronograph. In reality, we have IR screens, but in a field trial, we can't have the IR screens. It's a complex phenomena. So we placed a mechanism basically to measure the speed of the bullet just before it hits the panel, that is 2.5 meters from the panel to be tested. And to record how the entire event happened, we used to have a high-speed camera. So in this particular setup, this weapon is 6-AUR, this is a US weapon. At a distance of 10 meter from the panel, over there we have this ballistic chronograph as well. On the sides we placed a Motion Pro 7 high-speed camera basically. I'll share one of the result of this high-speed testing as well. But for now, let's continue with, if we tested n number of panels, can we have some sciences behind? So we developed a unique scheme for AK-47 at least, that on one side of, I hope you can appreciate that on one side of this central original core, that is unimpacted bullets, we cut the bullet and took out the steel part of it. On left side, I hope all of you can appreciate the heights are less compared to the right side. We analyzed if bullet is stopped, the amount of wear, reduction in length and reduction in weight can be very well correlated with a safe zone. So now we know that if the length of AK-47 core, residual core, is more than X, most probably it is perforated, proportionally there will be a weight as well. So we correlated that and we've established a relation. So it is this small 5.2 grams of steel which matters the most. If you have done everything, now let's better fine tune our simulation model, because we discussed at the very beginning that we don't have the properties, and whatever we use, generally we prefer that, okay, within the yield limit. But here everything will damage. So we optimize our model and we correlate that, okay, if I have a single shot phenomena, how does it goes? So we match them. And if things are moving fine, that's good. Good for us, or we can further optimize that. How about the mild steel core? So this is how a mild steel, that is a deformable steel, will look like when trapped inside the panel. So couple of slides back I've shown you a white colored panel. It is that panel only after hitting 8 shots of MSC, that is mild steel core AK-47, the bullets are trapped inside. They are very well deformed. Now the beauty is that with the first shot, the depth of penetration will be minimum. But as you move on, it will keep on increasing in terms of depth. Okay. Can we have NDT of the panel as well? Because ultrasonic C scan of UHMWP possible. But for the small pieces of tiles, it is impossible to go for ultrasonic C scan. So we used to go for CT scan. I hope majority of us knows what is CT scan. Known to you is for medical applications for human body. We used to use the machine for our ballistic panel before the test and after the test. So here you are observing those final panels where we cleared all the test protocols. 6 shots of sniper are fired and we can see that first bullet is somewhere over here, whereas the 6th bullet has gone much farther. Or the panel, okay, look at this particular curvature. It is pretty consistent. The extraordinary white top part is ceramic and less white part, where my cursor is right now, is the UHMWB part of it. And as the bullet hits the first and second bullet, there was a localized deformation. And as we move on, 6th bullet, the entire panel at the back has gone curved. And on the front face, now we observe that, okay, for this one I can see maximum damage. So maybe 4 or 5 tiles are damaged over here. But rest of the panel is still integral. Similarly, for this was for sniper, this is for AK-47. The issue with this kind of a system is human body is not flat. There is a curvature. So when we place the small tiles on curvature, there is a possibility of defective zone. I hope you can appreciate the gap over here. But fortunately, it is at the edge. So we have a lot of rules to follow when testing. So from any of the edge and in between any 2 shots, we cannot fire within a distance of 51 mm. Or simply put, no 2 shots can be closer than 51 mm. So from this edge also you have to be away by 51 and the tile is 30 mm. So this point is safe, but there was a defect visible over here as well. Defect in the sense that there is a minor gap between the 2 tiles. If bullet hits exactly at this point, there is a fairly good possibility that bullet will make out a way in between the 2 tiles. So the test agency will take an X-ray of this, will mark the exact spot where maximum gap is there and they will fire the bullet there. And that is what they call as the testing is always done under the most rigorous condition, because it's the question of life and death of a soldier. So we tested all of them. These are all post TMC, that is after thermomechanical conditioning. Or put it in a simple way, it is a panel which was made last month, but it has lived a life of 5 years. So after 5 years also all 8 bullets are stopped. The level 2 and 3, as I mentioned earlier, lead and mild steel, they are very easy to stop. So this is what we did in 2021. Back face signature is another important phenomena. We have seen deformation in these CT scans. So this deformation is to be taken up by the human body, and that's why we have a soft armor panel, something which I didn't discuss because that's a very easy job. Stopping a 9 mm bullet is like when you are dealing with sniper and AKs, stopping a pistol, which is a pocket held weapon, is very easy. Though it has got 600 plus joules of energy, so one bullet has got sufficient energy to kill more than one. Fire. So these were 4 shots fired. We all heard of what happened in Mumbai long back. So in case of automatics, this was a 6 or sniper, M80 ball. Yeah, M80 ball. The challenge is there will be a minor vibration because you are human. So when one bullet comes out, there will be a shake in the barrel and there will be impact on the shoulder. A cartridge could be of 20 bullets or more than that. If 20 bullets are moving as if droplets of rain, he cannot aim at one point. So what we did, the standard is 3 bullets. If you have to go for a burst fire, it has to be a burst of 3 bullets. But no trained army men having a highest experience of 23 years, he couldn't make it happen that 3 shots are fired and all 3 of them are on this single panel. So what we did, we divided this experiment into 2 parts. You can see here probably there is a left guy over here, left barrel, and there is a right barrel. So on the sound of fire, 2 bullets from left and 2 bullets from right, so that in total at least 3 bullets hits. And we recorded this phenomena at a speed of 10,000 frames per second. Other way around, how many rounds this weapon can fire. So when we say that, okay, this particular rifle can fire n100 or few hundred or whatever thousand number of bullet, this is what we mean. That you give a belt, either a bullet belt or a cartridge of 30-36. So within less than a minute time, your cartridge is empty. But there is a human in front of it. So this was the condition of the panel. So 2 bullets from left side and 2 from right, and all 4 are stopped at the back. What will happen with the human body? Now this sounds, it feels with the pictures and results that everything is good. Yet if we look at another panel wherein few of the conditions couldn't be met, because the standards will always say that, okay, this is the set of conditions to be followed or to be met. What if the bullet hits at a 25 mm? We said that it should be 51 mm away from edges and no 2 bullets close to 51 mm. But bullet won't follow, it won't hear. So if it touches the corner of a panel, something like this, it will lead to this kind of a deformation. Now this is a image from internet, of course. So this is what a 750 centimeter square panel looks like, the gray part of it. In Indian Army, the requirement is 1000 centimeters, so it is slightly bigger than this. Yet, if this kind of back face deformation is going to happen, it is more than sufficient to comfortably break the rib cage that will lead to immediate entrance of blood into the lungs or bursting of heart or liver. If that happens, that soldier was lucky guy because he died immediately. If there is a lung puncture, he will definitely die, but slowly. If he couldn't be taken to the hospital, and generally in their case what happens is that these jackets, I can't cover all the aspects of it, the jackets have a quick release mechanism. So within 3 seconds time, if someone is hit at the center, his partner or the co-army man, he will pull a string, the jacket is open. So his chest is open basically, visible. Within 3 seconds he can see, oh, you have got no blood. So you are good. But he can't stand because he has just now encountered 2000 or 3000 joules of energy. So that was a huge punch. So he will say that, okay, you be side of this wall, we have got an operation of 6 hours. We'll go 4 hours up and 2 hours down. And while coming back, we will pick you. And while coming back, most probably they will find a dead body. Even if he is alive, so much of blood has gone in and we don't know where is the base, how much distant it is. So the chances are. So there is a lot to be done yet. As far as rules are concerned, we follow the rules and we clear the test protocol. So jackets are to be designed like that. Somewhere we'll have to make a hard stop that, okay, we can't go beyond that. Like the discussions at the PAS or the International Personal Armor Committee level is that what should be the minimum distance between the 2 shots? What if the rain, that is that n number of this 100 bullets and 150 bullets per minute, if they are coming at a single spot or very close by. So there is a fight between the two that, okay, 51 mm or 25 mm. Because 25 is too close. We have seen the damage zone, which was pretty large. This is a simple one for your understanding. This is a video. Okay. This is a 9 mm bullet, pistol, which you normally see with any policeman. So this is a flexible material UHMWP which can comfortably stop the bullet. You can see the bullet as well. And there comes the second one. Now see the type of deformation it is going through. Though the bullet is stopped, the right side of the image, we can see the back of this panel, which is intact. There is no hole. So both the bullets are comfortably stopped. But if we look at this particular phenomena, how the fabric has bent, the time between these two shots is 0.05 seconds. The second bullet is coming much faster. And in case of rifles, it is somewhere around 0.02 seconds. The nth or the second bullet is coming. So what all we are looking for? We are looking for ballistic performance. The first target is please stop the bullet. Even if stopped, what is the blunt trauma? The deformation inside the human body is the blunt trauma. If it is beyond a limit in NIJ, that is US standard, it is allowed to go till 44 mm. They say that the US soldier has got a good healthy adipose tissue. So there the chest muscle, simply put, or the muscles are quite thick. But in Indian context, they are much thinner. So the limit is 25 mm. And 25 mm, though sounds good number, but it's very small when it comes to stopping the bullet. And in one of the slides, I have shown that for mild steel and NATO ball, we could stop the bullet within 10 mm of, or for NATO ball, actually it is 13 point something. But it is half of what the standards allow, 25 mm. Then how about the multi-hit? It's not just one bullet. We are going to fire maybe 6 or 8 bullets. We need a setup very close to the bullet itself. These setups are very, very costly affairs. And we need to measure both the entry velocity and if there is an exit, what was the exit velocity? There lies the rare of the rarest phenomena that bullet perforated, it passed the panel, but velocity was such that skin could or the clothes could stop the bullet. So still the life is saved. Then how about the comfort and ergonomics? So with the numbers of what we have, the jacket, basically it's all about the ergonomics of the drawing and the weight that matters. And we have been working on reduction of the weight. So I'll come to that in a couple of slides later. And then finally the environmental resistance. Kashmir is Kashmir, Rajasthan is Rajasthan, I can't help it, nor can you. There is a temperature, there is a weather, there is a moisture. So a lot of environmental parameters, they may also hamper the performance of a composite system. Even if someone is making it, then there is a second level of challenge, meeting all the compliances, certifications, agencies. So to get the certificate, unfortunately in Indian context, we don't have a certification scheme. NIJ, US and the West world, they have the certification. You once take the certificate and start producing till we upgrade the standard or we change the standard. So achieving this certification to be recognized as a ballistic standard is essential for manufacturer and supplier, first issue. Then adherence to these protocols is another level. If you are making these panels, you have to have quality assurance. So putting the long story short, when this army order is supplied, one truck will carry 5,000 jackets. 10 jackets will be picked randomly, and if any kind of failure is occurred, not about the only stopping the bullet, one of the backface signature turned out to be 25.1. It's just 0.1 mm. And we know from the recent news what is the impact of 100 grams from sports. So 0.1 mm of exceeding the limit is equal to 5,000 jackets rejected. And it's a huge cost associated with that. And then know the right market Even if you have certificate, you know all the quality standards, accessing the right market with the right certification is another level of challenge. So there is a strong need for specialized labs, dedicated specialized ballistic testing laboratories. In India, we have only two, one for defense, that is in Chandigarh, and fortunately one for home ministry is very close to you, is in Gandhinagar. Then we require highly trained, skilled staff. And that is where we are planning, we chip in that at research level, at PhD level and onwards, we have lot of composite stories. But when it comes to ground, who will operate the autoclave, who will operate the compression molding machine, who will perform all the cutting manufacturing operations, for that we require labor, the manpower on the floor, and that needs to be trained, and none of the PhDs will generally go to that level. So we need to disseminate that information, that knowledge to the next level. That happens to be the MTech. So we are in that phase that, okay, let's start with masters, then bachelors will know, and then only the things will percolate down to the shop floor so that we can produce the best quality composites, something which India is lacking till date. And that can be comfortably proven by the growth of the aerospace industries, which happened 2 to 3 decades back in the West world, which is pacing now in India. And accreditation. So I think we are very well known to them. At IIT Delhi, what we could achieve was that when we started in 2017, the Indian standard was a 10.4 kilogram jacket that was compliant to as per NIJ, because in 2017 there was no BIS. So we had a set of rules, a question paper you can say, that AK-47 hard steel core is the largest threat we have, and you need to decrease the weight of this 10.4 to somewhere around 8 kilogram. We were on that path, and 2018 came and BIS standard came. So there was a minor variation in the speeds of the bullet and types of bullet and whatnot. So actually the question paper changed in between when I was answering. And by the end of the project, that is somewhere in between COVID times, Indian Army said, we have no threat because of AK-47 now at the Kashmir part of it. So we are only interested in sniper now. Your front of the jacket should have protection against sniper. So again, the question paper changed towards the end of the project. So, and unfortunately for that part, there was no standard jacket available in India. So we could come up with, for both the solutions, we brought down the weight of a 10.4 plus kg jacket of 2017 Indian standard to 8.2 kilogram. It is 8 plus minus 200 grams it runs. So it is generally 8 to 8.2 kilograms. When we have a front of, as in this case we can see, it has got a front to protect the 1000 centimeter area of front. It is this part which has got AK-47 or sniper hard steel. A back, both the sides, that is both the kidneys you can say, the groin area and the throat. The throat has got full 360-degree protection against 9mm pistol, but only rifle protection is given to the front part of it. So this is what we could achieve, and this took us a bit of time. And this was done at IIT Delhi. Now at Ahmedabad University, we are coming up with all the facilities. You have seen the images of the cut section of the panel after bullet impact. So that requires a very precise machining process. So let me share some experience. We touched a tool, the fiber was pulled out. We tried laser. It was found to be solid state laser transparent. We tried with CO2, 150 degree was melting point, so we ended actually burning a lot of material. So finally we could optimize with water jet. Water is the best material to cut this panel, and water is the best material to cut the food as well. So we are going to have that facility as well here. We are going to, at this campus, we are going to have water jet and compression molding for MTech composites. And for autoclave, we are having a tie-up with Atira. They are having this, they are in the process of getting this large commercial autoclave, because they are primarily into the parts for ISRO. So what and where is the future? Yes, we are looking for increased protection. What should be the ideal weight for a bulletproof jacket? Or what can be the ideal material for bulletproof, if I may? Air is the best possible bulletproof jacket. The solution is, if there is a rifle, it has got a range of 500 meters, you stand at 800 meters, air has got sufficient resistance and earth has got sufficient gravity, the bullet will fall. But army man can't say that. So we could pull it from 10 plus to 8, and the army says that why can't you make it half kg or 0 kg kind of. So there lies a lot of scope in that domain. Then enhance comfort. If you are given with a 1 inch or a 20 mm thick plate in front of your body and something on the side and back and neck, you just can't move your head like that with all the safety gears in place. So comfort is another important thing that is only possible when you decrease the thickness and decrease the weight. So there again lies a lot of scope. And then integration of technologies. That is something which everyone is talking, but not much is going on that front. So a lot of scope lies on front of getting the real-time data. What kind of health he is having. Like a CO sitting at the base, he says that you have crossed that peak and now you start firing. He says that, sir, I have climbed 200 meters and now I am dying for the breath. So the comfort has got a role. So why can't we have the integrated medical technologies that CEO knows that out of these 8 men, how many are in what condition, or all of them for that matter. Accordingly, he can plan the strategies better. Likewise, after the shot, what is the condition? And why to have a shot? Why not to have more gadgets inbuilt into that? So that is what I expect that in future, that is here at Ahmedabad, I am going to have a bulletproofing facility. We are in progress of that in composites, we will start more studies on the composite materials, then incorporating nanotechnology. Like in the morning session, Bitra director, he mentioned that not just the carbon fiber, they have incorporated 0.05% of CNTs into the fiber that will enhance the properties like anything. So if we can incorporate that at the commercial level, the weights will come down drastically. Biomimicry, what commonly known is that self-healing or self-repairing kind of phenomena. So on those directions also, or at least repairing the BPJs, because the BPJ plates cost a lot. So if one bullet is hit, we say one life is saved. That is one part of it. But then a huge cost is gone. Apart from that, the development of more and more lighter, more and more flexible and self-healing coatings, so that the material can take care of itself, and with lot of integrated sensors if we can have, nothing like that. So on that front, yeah, I would like to take few moments extra. We at School of Engineering are very soon going to have a learning factory, wherein a fully automated factory floor will be coming into existence, and KUKA robots, they are supplying us metal printers, not just the 3D printing by polymers, but metal printers will be coming up. Basically, it will be a place, it is going to very soon, a place wherein the staffs can be trained or will be trained to work in a fully automated factory, which could be a manless, only programming is to be done outside. Then how the entire factory scenario, the modern world works like. So we are working on those lines to have a world-class facility here. In terms of bulletproof, coming back, in technology world, we have a term called as TRL level. So generally, or even in last one and a half day, you must have seen many of the technological outcome, that is the outcome of research, is presented. That lies somewhere around basic principle and a concept and a proof of concept at the max. So we say that, okay, the TRL level is 1, 2, 3, 4, that's it. The education institutions generally don't go beyond that, but we at IIT could deliver. It took a bit of time, but now we have all the relevant experience. So we have integrated pilot system demonstrated. The product has complied and met all the standard requirements, and now it is going to the private players for mass production. And that thing is a closed chapter Now we are here, we are going to further continue on that journey, that why can't this 8 kilogram be bring down to 7 kilogram and 9 plus kilogram to whatever less we can. Of course, academics will never go for mass production. That is the responsibility of the private limited companies for that matter. So from that point onwards, we will hand it over to the industries, and for that, we wish to collaborate with the industry partners, as my colleague Professor Shyam mentioned, that you promote your staffs or sponsor your staff so that they can be here for 2 semesters, study the composite, and then take up your projects. Not necessarily bulletproof. It cannot be everyone's field of interest, but it could be your area of interest. So this is what we could do, and this is one of the recent ones wherein at IIT Hyderabad, I presented it to one of the minister. What is his name? Dharmendra Pradhan. Is there a mistake? No, I'm asking you to think. So you please think what directions we wish to move. Shall we be static? No, definitely not. All those who are in this hall, they are definitely desperate and sincere towards the growth of composites and towards the growth of their own career and industry. So this is the right time that whatever area we are into composites or integration of technologies, as Professor Shyam also mentioned that he is using the technology. So when he says EV, it has got both. Composite is there and there is automation. So is the dean mentioning that, okay, we are going to have a factory of future. That is the learning factory with all automation in that. So I welcome you all once again. And if you have any questions related to bulletproofing or any other subjects, I'll be more than happy to help you out. Thank you. Sorry, third one is boron carbide. Okay, yeah. But that is not, that was just the initial trend some 12-15 years back when it started. It turned out to be a very good material. I got your point taken. I mean, I hope if it is not answered, then do let me know. UHNP was growing, so was PBOs, but PBO turned out to be because of the environmental factors, it degrades very fast. So that was the challenge with that. So it was, it came very fast and it fall down very fast. Anything else?
You have mentioned that when bullet hits to the ceramic panel, so it will crack suddenly from that point of.
Yeah, radial and circumferential.
Have you done any damage mechanics or fracture mechanics study when that propagates and how it will damage the system?
We did try it, and we have a camera which has got a speed of 10 lakh frames per second, and we found that 10 lakh is too small a number. Oh, sorry, 1 lakh. 1 lakh frames per second is a small number. We require more than 3 lakhs frames per second to track or to measure the speed of growth of crack in a piece of glass. I request those who are students, if here anyone, and if you happen to find a piece of glass somewhere in the scrap piece, place it away, try to strike it, record it, and let's try to see what is the speed of propagation of crack, how fast the glass breaks basically. So we attempted and we found that we require even higher speed cameras. It is going in lakhs, but we can't measure that. I mean, with the facilities we have, we couldn't. But we did store that, okay, first this crack goes out and then circles are formed. So circumferential and radial thing is clear, but speeds are to be measured. Anyone else? Yeah, please.
Can we use polyurea? Polyurea resin.
Any and every material is good for bulletproofing. You'll have to only increase the thickness. In here I said that much of thickness. In UHMWP, the beauty is, like if I have to share a number, 1.2 kilogram and 13 mm thick is the requirement for UHMWP for a specific grade, 13 millimeter. It's more than sufficient. If I go for Kevlar, this will be about 20 millimeter, well above 20 millimeter. Right? And now if I keep on decreasing, I have shown one of the figure wherein I have mentioned the modulus and tenacity both are rising. So if I go for steel, I'll have to come down. That means the weights will increase or the thickness will increase.
Because polyurea has excellent blast proof properties.
Yeah, that is right. There we are playing with the blast wave. So you need to stop the shock wave and the blast wave. The wave is being stopped by the foam part of it. But how about the sharpness or the projectiles? For that we require this kind of material only. Thank you.